Shlomo Zilberstein.
Thank you. Hi, everyone. So this was work done at UMass Amherst with Professor Shlomo Zilberstein, as Raul said. So I'll get started. So as many of you know, there's been an interest in reduced models for planning in probabilistic domains. Some examples are models that aggregate states using some notion of equivalence, or, for example, by limiting plan reachability to a certain envelope. We saw some domains yesterday, some examples of reductions yesterday in the workshop, like Ron and Brafman talk. And in particular, there's one type that is interesting for this work, is determinization. And it's a very simple idea. We take an MDP, we create a deterministic version of the MDP, for example, by always choosing the most likely outcome, and then we solve it using a classical planner, execute the plan. If we reach a state that was outside the plan, we replan and repeat this process. And this approach became very popular after the surprising success of FF replan in the 2004 probabilistic planning competition. And well, later, based on this idea, the people developed more robust approaches like FF hindsight, RFF, HMDPP. Now, even though it's appealing because we can plan faster, there are some drawbacks to this approach, as with any methods that considers outcomes in isolation. So they can be overly optimistic because they ignore risks, or even if all outcomes are considered, like for example, the so-called all outcomes determinization, it could happen that the planner will choose an action that seems promising just because one outcome looks good, even though there might be other outcomes that are more likely and there might be bad. So overall, any of these approaches can produce plans that could be arbitrarily worse than an optimal plan. However, it's an appealing idea to have a simplified model that we can use to plan faster. So here we introduce a more general paradigm in which the single outcome variant of FF replan is just one extreme point in a spectrum of MDP reductions, and these reductions differ in one of two dimensions. The first one is the number of outcomes per state action pair that we fully account for in the reduced model, and the other is just the number of occurrences of the remaining outcomes that we planned for in advance. Our formal framework is stochastic shortest path problems. It's an MDP with a start state and a set of goal states, and the objective is to minimize the expected cost of reaching the goal state from the start. We also consider factor representations of MDPs, for example, PPDDL, where actions are represented as probabilistic operators of forms such as the one in the slide, where we have some preconditions, some cost, and a list of probabilistic effects, each one associated with some probability. And over this, we introduce some concepts of primary and exceptional outcomes. So like I said before, the reduced models are characterized by two key parameters. The first is the number of primary outcomes that are fully accounted for. So we call those primary. And all other outcomes we call exceptional outcomes or exceptions. And we plan for a bounded number of exceptions in advance. And this is an idea that's being explored in the context of fault-tolerant planning, work by Jensen et al. Or Carmel Domschlag, and some work we also presented at ICAPS last year. Now let me give an example of these MDP reduced models. So take a simple problem at the top, and we have, let's say we have one type of actions, and I label the outcomes by red and blue. So there are two possible reductions. One is by choosing red as primary, the other is choosing as blue as primary. And let's say we plan for just one exceptional outcome in advance. So the exceptional outcomes are the ones with dashed lines. So we can have two possible reductions, right, depending on whether red and blue is primary. The one on the left, we can see the one on the left has blue as primary, the one on the right, red as primary. Now, one advantage of this reduction is that although it might seem that we might complicate the problem, actually the size of the reachable state space becomes smaller. So for example, on the left, the white states are no longer reachable because we need 2 red outcomes to reach any of those states. So we actually, the size of the reachable state space can be reduced. And this is beneficial for search-based algorithms such as LA star, labeled RTDP. So this is a key idea that we want to take advantage of. The way we do this is by using an augmented MDP, where each state is associated with a counter of how many exceptions we've seen so far. It's bounded by K. The initial state, of course, has no exceptions. The costs and goals remain the same, just with the added counter. And the more interesting part, I think, is the transition function, right? So we have a set of primary outcomes, and I'll talk later how can one choose these primary outcomes. But say we have a set of primary outcomes, PA. Now, when we reach a state that has the counter up to K, which is the bound, then we assume that exceptions can no longer occur, so the transition becomes 0 for those states. And the remaining probabilities is distributed among the primary outcomes so that they sum to 1 again. When the counter is less than K, then it's just the initial transition function, but we update the counters appropriately. So if a outcome belongs to the set of primary outcomes, we don't increase the counter. If it does, we increase it. Now, using these equations, we can define a MKL reduction as just an augmented MDP where the counter is bounded by K, and for each action, we consider at most L outcomes. So for example, the single outcome determinization of FF replan is just an instance of a M01 reduction, where each set of primary outcomes only has the most likely outcome, and we plan for 0 exceptions in advance. Of course, for a given K and L, there could be multiple reductions, so these are distinguished by characterized by 2 choices. One is which outcomes we label as primary, and the other is how to redistribute the probability of exceptional outcomes among the primary ones. So in this work, we simply renormalize the probabilities so that they sum to 1, but there could be more sophisticated approaches like using some notion of similarity between the exceptions and the remaining primary outcomes. But here we just normalize. And you may have noticed that if we take an MDP, apply a reduction, and then use that for planning, the resulting plan is not necessarily complete because the reduction, as I say, might cut the size of the reachable state space. So if we use that for planning, we might reach during execution a state that wasn't considered in the original plan. So we use here a continual planning approach. Essentially, what we do is we take an MDP, and given some KL and some set of primary outcomes, we solve that reduction using a search-based algorithm. We use LA star for this in this work. And if we reach then execute the plan. If we reach a state where exactly K exceptions happen, at that moment we trigger replanning. And notice that the reason we do this is that for that state we will still have a plan ready, but it could be the case that after executing one action, we reach a state that had essentially another exception, so we will be out of the plan. So in the example, if we use the model that was on the left, you may recall, if we reach the state in red during execution, at that point, after executing the action, the blue action, we might reach the state in green, which wasn't in the original plan. So it is at that point that we trigger replanning to anticipate any possible outcomes that weren't considered. And we do this in parallel to the action being executed. So we replan at the same time we are executing that action. This is just one approach. There could be other continual planning approaches that we can be improving the plan since we start executing. We could use, instead of replanning at K, we could start replanning as the first exception happened. There are many possibilities. But one appealing property of using this approach is that we can actually compute the exact value of the resulting plan, which is appealing because many times with continual planning approaches, we have to evaluate empirically the policy. So I won't go into the details for the sake of time, but Essentially, we can construct a Markov chain that simulates this continual planning process and give us the exact value for a particular reduction, the value of using the resulting plan on the original problem. Now, I may say that this is a costly process. We need a universal plan for the augmented MDP, which is harder than just solving the MDP in the first place. But we will use this later to learn a good model. I'll get to that later, shortly. So let's see some examples. One example is the racetrack domain. It's a well-known reinforcement learning benchmark. We added some additional parameters. Particularly, the most important is that we introduce some errors in the actions that can be taken. So for example, if I try to accelerate in one direction, it could turn out that I accelerated in another direction. And this can happen, although, this can happen anywhere in the racetrack. Okay, that's one example that we work on. And we also work on the triangle tiewar problem. There's a graph, and the agent has to reach the goal from the start. The complication is that the car can get a flat tire, and then if it doesn't have a spare tire, it gets stuck on that position, right? So the optimal plan is to go through the path that always have a spare tire, which is the path with black vertices. Now, one question we can ask now that we have this framework of reduced models is whether determinization is good sometimes, or is it always good? So here, when I say determinization, I'm talking about 0-1 reduction. So one outcome, no exceptions planned for in advance. So we experimented on the racetrack domain to see, even if we completely ignore exceptions, what happens if we have more than one outcome in the reduction instead of just one. So we compare on the left the best determinization for this problem, which is simply choosing the most likely outcome, versus the best possible 0-2 reduction. That means, ignoring exceptions, 2 outcomes. And we can see that there is a large increase in cost when we simply use determinization. So just adding one outcome, even though I'm ignoring all other outcomes, pays off. Now, another question is whether determinization can sometimes be actually beneficial, can actually be optimal. So that comes up with in the other example, in the triangle tiewar domain, where it turns out that if we choose, there are 2 options. We can always assume that we won't get a flat tire, or we assume that we always get a flat tire. And it turns out that if we use the determinization in which getting a flat tire is the primary outcome, in that case, we can get the optimal policy by being overly conservative, because the planner will just simply choose to go where there's a spare tire, right? So the problem is that so if we use typical heuristic that I use to choose one outcome, it's usually the most likely outcome, or maybe the most desirable outcome, right? But in this case, none of this work, because getting a flat tire is not the most likely option, and it's also not the most desirable one. So intuitively, one could think that the primary outcome should be not getting a flat tire, because it's the desired condition. So one could always try to always plan conservatively, so choosing always the most undesirable outcome, but that doesn't work either. In domains such as the racetrack, that doesn't work. So the question is, do we need a more principled approach, a value-based approach? And in this work, we give an initial step in each direction in which we generalize from small examples. We create small problem instances for which reduced models of any size can be solved, and then we explore the space of reductions and find a good one, and then apply that reduction to larger problems. And it's still an open question in which conditions this can be done, but for our experiments, this worked well in practice. More specifically, we have a greedy method. We start with a full model, and then, so for a particular a small instance of a domain, We start with a full model, and then iteratively, we remove one outcome by computing the exact value of the resulting reduction using the approach I described earlier. And then we continue this process, removing one outcome until either a certain parameter in the number of primary outcomes is reached, and increase in cost or decrease in value with respect to the previous model is reached. And this is some predefined threshold. Because we can actually reach the bound on primary outcomes, but if the increase in cost is not too large, we can keep going and end up with a simpler model. So here are some experiments on the racetrack domain using this approach. We had a racetrack with 30-something thousand states, and we learned the model using a racetrack with 1,000. And here, we are interested in the total cost of reaching the goal, but accounting for planning time, because our motivation is to try to reach a plan that is close to optimal, but as fast as possible. So here we introduce a trade-off between planning and execution, where we assign some action cost to the planning time, and that's what the total cost in the lower table shows. So we can see that CPU time is much faster for that, and M02 are just ignoring exceptions. That is M01, like a model with just one primary outcome. 2 means 2 primary outcomes. We can plan much faster, but when we see the actual cost of the policies, it increases a lot with respect to using a model in which we plan for one exception in advance. And in the case of the 2 models on the left, it's just the 2 planners, just value iteration, and Elliott start using the full model. In that case, although we get the optimal policy, the planning time offsets any gain that we can have with respect to the optimal cost. And we can compare this with a lower bound, which is the best case, is getting the optimal plan with 0 planning time. That would be the best case scenario. So this compares every algorithm against that bound. And we can see that using planning for one exception in advance gives us, it's within 5% of this lower bound in total cost. And it's larger for the other algorithms. So finally, we also, I'll be brief here, we also introduce a way in which we can take advantage of existing planners using a PDDL compilation in which we tag a PPDDL file with a set of primary outcomes and generate a one reduction of the PDDL. So, sorry, not one. The number of primary outcomes depends on the tagging, but we only consider one exception in advance. So case 1. And we can talk about it offline or during my poster later on. So, but the advantage is that we can use this on any planner that can read PDDL files. And we tested this using some IPPC from 2008 domains, Triangle Tiewar, as I mentioned, Sino Travel, and Bloxworld. And the figure shows the number of instances that the planner was able to solve in 20 minutes. And although we didn't perform a direct comparison, these are comparable with some of the state-of-the-art that has been reported for these domains, particularly Sino Travel and Triangle Tiewar. So in conclusion, we introduce a new family of reduced models that can play a very useful role in planning. They're amenable to exact computation of the value of the resulting policies. We can use a standard MDP solvents via a simple compilation scheme. We showed that determinization works well in some domains, but it's not always. Typical heuristics to choose determinizations don't work well in practice or might not work well in practice. So we introduce a value-based approach using small instances and generalizing the model to larger instances. And for future work, we are exploring more efficient strategies to explore the spaces of reduction for a particular problem instance instead of a particular domain. And there are some other open questions related to how to redistribute probabilities among primary outcomes. And that's it. Thank you very much.
We have time for some questions.
So can you explain a little bit more about the?
Go ahead.
Sorry, a bit more about the learning.
So
That generalizing.
Yeah, so the instances are not automatically generated, so we give them the small instances, and then we simply take the value, the way we can compute the value for the reduction. We start with a full model, compute the optimal value, and then we try. So let's say you have 3 actions, and one with 3, one with 2, one with 2. So we have, say, 7 outcomes in total. We choose one of those from each outcome, from each action, try them all, and choose one, the one that has the lowest increase in expected cost.
How do you generalize to larger instances?
Well, that's part of the open questions, right? In what cases we can do that, in what cases don't. In the racetrack domain work, in this IPPC domains that I tried also work well. I learned the more we found the model by doing the same process of trying, starting with a full model and see which outcomes. So,
Malik?
Just clarify the answer.
Once-
The reduced model applies immediately to problems of larger size. There is no need to generalize it further.
yeah. So we learned the reduction is generated, and that's a reduction that's used for the larger model. But in what cases that works well,
It's an interesting approach. Have you looked at how you can relate your approach to other approaches of sparse probabilistic planning, where some of your actions are deterministic, some are not, and you do path compression in order to benefit from the sparseness of the non-determinism? Have you considered relating your approach or benefiting from their techniques or extending with variable k in your case with respect to that?
Yeah, so it's not necessarily tied up to any of the algorithms that, for example, Heliostar, or I think this can be coupled with other solvers, and there are approaches that prune actions based on some notion of helpful actions. So I think it can be combined with approaches such as the one you mentioned. I don't know if yeah.
One more question. Okay, if not, let's thank you.
Thank you.